Okay, I should really quick teach you guys how to do some specific heat problems. So the people that aren't here, I can give a quiz on Wednesday and they'll all be screwed. But I think it'll take me a little bit of time before I get there. Because what I want to really get done today is to really get a handle on the terms heat and temperature as they're used in physics in a precise sort of way. Because it turns out that they're not the easiest words to define really, and that the way we use them in everyday language is sometimes somewhat interchangeable and sometimes a little bit inexact. And we want to
Draw a distinction?
We want to draw a distinction between the words, and we want to make sure specifically when we use the word heat that we're using it correctly, because it is a tricky word and it's hard even for me to give a definition of the word heat that's precise. We talked about the word force a lot, and especially in the readings in the book about how to use it precisely. Heat is, I think, even harder to use precisely. So we want to try to get to a point where we understand those words by the end of today and can use them in a way that's exact from here on out. Just to make a distinction between theories of heat historically. Last time we talked about the difference between ancient theories of heat, which involved heat as a type of stuff, and heat as a manifestation of motion. And the dividing line between these two things, I don't really know if one could draw a clear dividing line between them, because it doesn't happen smoothly by any stretch of the imagination. But sometime between the middle of the 1700s to the middle of the 1800s, there's a shift from thinking of heat as a kind of stuff to thinking of heat as a manifestation of motion. So we call this the substance theory of heat, or the caloric theory of heat. Where heat is the present or absence of this mysterious, invisible, weightless fluid called caloric. And we refer to the more modern idea that heat is the motion of the microscopic parts of an object, kinetic theory of heat. So when I say the kinetic theory of heat, what I'm talking about is the idea that heat is nothing more than motion, and we can equate that in the modern conception of physics with the motion of atoms and molecules, that at the subatomic level, the microscopic level, what matter is little atoms and molecules, and those atoms and molecules are in some way moving around, and that motion may be different in solids, liquids, and gases, and we can talk about the ways in which that's true. But in some sense, how hot something is, and I'll try to not use, since we're not being precise just yet, I'll try to not use the word heat or temperature. I'll just simply talk about how hot something is a measure of how fast its parts are moving. If you believe in atoms, we can call those parts atoms or molecules or whatever. So the kinetic theory of heat doesn't quite demand that we believe in atoms, but sure is a heck of a lot easier to understand what's moving if we believe in atoms. The thing doing the moving are these smallest parts of matter that have been postulated since the time of the ancient Greeks, but we're only starting to really, really sink our teeth into the idea of atoms in the 1700s and 1800s. So our understanding of heat as a kinetic process parallels our discovery of atoms, what the chemists are doing across the hall during this time is figuring out that there are these substances that cannot be broken down any further, that there are, whenever you mix things together chemically, the products and the reactants always have fixed proportions to one another, which suggested to Dalton and others that there were these smallest units of chemical change that we now think of as atoms. So when we talk about something heating up or cooling down in the kinetic theory, instead of talking about some substance which is moving out into the air, we have to reconceptualize what we're talking about in terms of motion. We said, for example, that if you bring a cup of coffee into the classroom, that starts out hotter than the air in the room, that over time, let's say it starts off at 150 degrees Fahrenheit, and the room is 75 degrees Fahrenheit, that over time the heat in the cup will be in some way transferred to the air in the room. It was easy to talk about what was going on there when we regarded the heat as a type of stuff. The stuff that was heat simply leaves the cup and enters the room. How do we think about this process in the kinetic model? What is happening? What is being transferred to what and how?
Well, the energy that's like the kinetic energy in it is being dispersed amongst the air particles around it.
How? How does the energy get from the water molecules in the coffee to the air molecules?
Like a big fight.
Well, expand on that. What do you mean by that? What is actually, if we could zoom in right here on the interface between the coffee and the air, what would we see? We would see a bunch of air molecules up here. We can represent them as just, they're mostly N2s, right? They're 75% nitrogen molecules in the air, a couple of O2s. Okay? Down here we've got mostly water molecules. Your coffee is mostly water. There's some other big, nasty, tasty organic molecules in there as well. Probably some sugar molecules. Hopefully a couple of sugars in there. But it's mostly water. What's happening in terms of the motion of those things? Which ones are moving faster?
The air. The water and the sugar.
Okay? The water molecules have greater kinetic energy, right? How do we know? Because they're hotter, and that's what it means to be hotter. So these are moving more quickly. These are moving more slowly. The air molecules have more freedom to move. In other words, they're further apart, so they can move further before banging into something else. But in terms of their kinetic energy per molecule, the water molecules in the coffee are moving faster. What happens here at the interface? What happens every now and then? They bump into each other. And when a fast-moving ball bumps into a slow-moving ball, think billiards, what typically happens if they're about the same mass is that some of the kinetic energy of the fast-moving ball, when it recoils, gets transmitted to the one that was moving slower. And the one that was moving slower moves off more quickly, and the one that was moving fast rebounds more slowly. So one collision at a time, the fast-moving molecules in the water are transferring their kinetic energy to the slow-moving molecules.
So it's
in
just
the air.
a momentum thing.
It's just a momentum thing. It's a conservation of energy thing. It's happening in the walls of the cup. In other words, the kinetic energy of the water molecules is banging into the molecules of the ceramic or the plastic or the stainless steel or whatever your mug is made out of and causing them to move more quickly. Now, because this is a solid, the atoms and molecules aren't free to move around amongst themselves. You can think of the walls of the container as more like a bunch of molecules connected to one another by springs. They're not free to change their relative position with respect to one another very much, but they are free to vibrate, and they are free to move about their equilibrium positions. So when one of these water molecules bangs into one of the molecules in the wall of the cup, it causes those molecules to vibrate. That heats up the cup. If there's an air molecule out here that happens to bump against the vibrating molecules in this cup, it gets a little kick from that wall and it moves up away more quickly.
So things like metal, as they get really cool, they get smaller, right?
Yep.
So that's just because there's an absence of movement. Everything kind of just rests.
Well, yeah, I mean, there are opposing forces when you've got, there are attractive and repulsive forces between these molecules, and they will reach a sort of equilibrium of distance between one another that they're most comfortable. if you get them moving faster, well, let's ask the question you asked. It's a better way to think of it. Part of where that equilibrium is depends on what their kinetic energy is with respect to one another. If you cool this thing down so they're moving more slowly, those attractive forces can pull everything closer together. So if the things are less sort of agitated in their motion, they will fall, they will reach this equilibrium distance at a closer distance to one another. And the same thing goes for gases. If I take a gas like this and heat it up and everything's moving around faster, they bang into each other more often, they push each other apart, so a gas that's heated up will expand. And same goes for a liquid. The only real big exception to that is water, which you probably know, does not, when you freeze it, actually expands a little bit relative to liquid water. Liquid water reaches its maximum density about 4 degrees Celsius, and then it expands again as the water freezes. And that has to do with the fact that water is a polar molecule, and when it settles into its crystalline structure, it's actually closer, when they're liquid, the molecules are actually closer than when they crystallize and they sort of make this hexagonal structure with respect to one another. Yeah, they actually push each other apart. So the water gets less and less and less dense, and then more and more, lighter and lighter and lighter.
It's that the O's are kind of
It's the repulsive force between the H's. It's the hydrogen bonds. And you know, if you take Bobani's chemistry course, she will explain to you why that's essential for a lot of the properties that make water important for living organisms. In fact, in the Life in the Cosmos class I'm going to teach next semester, we talk a lot about, you know, why do we consider water to be an essential ingredient for life? And one of the reasons is that the fact that it has, well, speaking specifically this property of its density, the fact that that ice is less dense than water, that an ice cube floats in water and doesn't sink, is actually pretty essential for life on Earth. If water froze from the bottom up, lakes and small seas would be completely frozen in the winter. Instead, what happens is they freeze, ice floats to the top freezes, and that insulates the water underneath, and things can stay alive for the whole winter. If water did not do that, a lake would not be a very good place to live when it froze all the way through solid to the bottom. So it turns out that the chemical properties of water are unique and important, and it's kind of what makes water water, that it has these properties that make it good for living in and being made out of if you're a living organism. Anyway, so the thing to keep in mind about the kinetic theory of heat is that it is a random process. In other words, we treat the collisions between these atoms in the water and the atoms in the air as pretty much happening entirely at random, and the process is a one atom at a time transfer of energy. We'll talk about that randomness a little bit more next time in the class after that, when we talk about the modern treatment of kinetic theory in terms of something called statistical mechanics. But for now, I want to stay focused on this. The mechanism of heat transfer in the kinetic model. When does the heat transfer stop? When does the cup stop transferring heat to the room? At the same temperature. Now the question is, first of all, why? Okay. What must that mean to say that they're the same temperature? In other words, what are we saying about these molecules and these molecules?
They're moving at equilibrium.
They are moving at either the same speed or the same kinetic energy. We have to think about really carefully what is the same about them. But when they collide, these are just as likely to transfer energy to these as these are to transfer energy to these, right? So yeah, every once in a while some of these will be moving a little faster and some of these will be moving a little faster. But on average, just as many water molecules are kicking the air molecules around as air molecules kicking the water molecules around. So they have the same average speed or the same average kinetic energy. Something about them has evened out. So the important thing to realize about temperature is that when we talk about the temperature of something, we are talking about a property of the average particle. When we talk about how hot or cold something is, we're talking about something about the material in bulk. Okay? Here's the difference between heat and temperature. Suppose I go to Starbucks and I get me a you know, a big, super gigantic, venti, hot beverage of some sort. That's how hot are the drinks you get from Starbucks? It seems they're about 190 degrees Fahrenheit, right? And suppose I have a teaspoonful of the same beverage. Okay. Which one would you rather drop into your lap? A teaspoonful of coffee or the entire venti, gigantic thing of coffee? Yeah. Why? It's still 190 degrees Fahrenheit, right?
There's less like gross energy.
Yes. Less total, what we would call thermal energy. It has the same temperature, but there are fewer atoms and molecules in that teaspoon of water to transfer their heat to you, right? And I used the H word again. Damn it. We don't want to use that H word until we define it precisely. There are fewer water molecules in that teaspoon to transfer their kinetic energy to your molecules and burn you, right? I mean, that's what's happening when you dump a whole cup of coffee on yourself. You're dumping a bunch of fast-moving molecules onto your body, and they're transferring their kinetic energy to the molecules in your skin. And that can actually break the cell walls and damage disrupt the proteins that make up your cells and actually physically cause damage to those cells. So the word we use in science for quantities like this, or the distinction, much like the distinction between vectors and scalars, is intrinsic and extrinsic. An intrinsic quantity does not depend on how much stuff you have. And an extrinsic quantity does depend on the quantity. So think about the difference between mass and density, right? The mass of something depends on how much you have. But the density of something does not depend on how much you have. You got a piece of wood that weighs 5 pounds, you cut it in half, both halves still float, right? They both have the same density. So density versus mass, and the temperature analogy is temperature versus total energy. So temperature is an intrinsic property of a substance, of a system, let's say. It is a measure of the average kinetic energy of the atoms and molecules in the system. Now we just said that, well, we said a couple of things. Let's recap. First of all, we said quite a while ago that energy is always conserved. And we are now saying that heat is a form of energy. That the kinetic energy of molecules is kind of what heat is. Or we haven't defined heat yet, we'll call it, heat is a manifestation of kinetic energy. That what's going on when something is hot is that the little parts of it are moving around really fast. Okay. How do we know that for sure? How do we know that this thing we're calling heat and this thing we're calling energy are the same kind of thing? The big experiment that is credited with, quote unquote, proving this or demonstrating this or testing the assertion that energy and heat are the same sort of thing, was performed by James Joule. This is why the unit of energy we use in the metric system is called the Joule. And what Joule did was a very simple experiment involving a container of water and a paddle wheel. The weight. And what Joule did is he carefully insulated this container from its environment, closed it up, put a lid on it, and let this weight fall a certain distance, which represents a change in what kind of energy? The weight, m times g, times the height that it changes, we call what? What kind of energy? Specifically gravitational potential. So we can measure, if we let this weight fall, how much its energy has changed. Where does that energy go? The weight started here, it winds up here. That energy has gone into this paddle wheel that turns around and turns around and turns around. When it stops, the paddle wheel stops. Where's the energy? In the water, in the form of heat, supposedly, if this is what heat is. And then he cranked it up again, he let it fall. And he cranked it up again, he let it fall. And he cranked it up and let it go and fall. And he measured the temperature of the water. And what he found was that the amount of work done and the amount of temperature change were proportional to one another. That there was a linear relationship between how much work he did on the water with the falling weight and how much the water changed temperature. We could express this as the work done is equal to the change in, I don't want to use the word yet. We'll just say work. Transferred from one to another. This experiment is often referred to as the mechanical equivalent of heat. It has been on my to-do list for many years to buy some apparatus that we could actually do a lab and measure this. It's a fairly simple apparatus. It consists of a little metal cylinder, about this big, that you fill with water, and you wrap a string around it, and you hang something really heavy off the bottom, like a paint can full of sand or something that weighs, 20 pounds or so. And you turn the crank such that you're exerting enough force to suspend that paint can in the air, and the friction between the string will heat up the cylinder. This has got a digital thermocouple in it that allows you to measure the temperature very, very precisely. And then you equate the amount of energy you put into holding that up with the change in temperature of the water inside the container, and you show that the amount of work you did and the amount of heat that's produced are proportional to one another. Another even simpler version of this I saw is just like a bag full of metal chips, like a Ziploc bag full of metal chips, and you just keep dropping on the ground over and over again until, and with a little thermometer inside, that it will gradually heat up, and you multiply the number of times you dropped it times the height, figure you dropped it from a meter, and the change in temperature should be proportional to the number of times you lifted it. They're all versions of Joule's original mechanical
What's
equipment.
interesting is like with ice cream, like to get it to be kind of creamed and icy, you have to churn it.
Yeah, well that has to do with the fact that you're actually, because the salt and ice mixture is actually drawing heat from you're lowering the
You're stealing from one and giving
Yeah,
it to the other.
yeah, and we'll talk about freezing and melting is a little more complicated than this because it involves a change of state, and we'll talk about that. We might get to it by the end of class today. So there's a little more complicated stuff going on because when you melt something, you've got to break those chemical bonds or the molecular bonds that are holding adjacent molecules to one another. And so some of your energy has to go into that. So Joule tells us that heat is a kind of energy or a manifestation of energy. And we can, if we believe that we're on the right track in figuring out what heat is, we're going to call this the first law of thermodynamics. The first law of thermodynamics is that energy is always conserved, or that the change in work of the system is equal to the change in heat of the system. Maybe that's how I'll phrase it. The work done on the system is equal to the change in heat. Even though we haven't really quite yet exactly precisely defined this word. There's another law of physics that we stumbled on when we described this scenario. That heat seems to know which direction to go in a physical system. And we call this law the second law of thermodynamics. And the first and simplest way to phrase the second law is that heat will only spontaneously flow from a warmer object to a cooler one. Now, we're cheating a little bit, because we use the word heat, which I just said we haven't exactly entirely defined just yet. And we're using the words warmer and cooler, which has something to do with temperature, which we also haven't exactly precisely defined yet. There is no noun for this one to refer to, is there? So let's try to pin down this word temperature a little bit. We just said a little while ago that heat will no longer be transferred from the formerly hot coffee to the room when these two things are the same temperature. How would you know that has happened? Physically, how would you know that the heat from the cup is done flowing into the room?
No difference.
No difference between what and what?
Put your finger through it.
You put your finger through it. Do you think your finger's the best tool for the job?
No.
No. What's probably a better tool for the job?
Thermometer.
A thermometer. Okay.
Or your
What-
wrist.
Yeah, right. Well, we'll talk about in a minute why that might not do it. But you put a thermometer in here, and you check to see that they're what? The same temperature. What does that mean? Here's my thermometer. Okay? Here's some water that's been in here for the whole class. So one would suspect that it's about the same temperature as the room. What would I do to verify that that was true?
Have two thermometers, one inside, one outside.
Okay, I could do that. I could get my other thermometer over there. And what would I do with them?
Monitor.
Okay? I mean, where? What do I have to do with it?
Read it.
Okay? 15, 16 degrees. What does that tell me? Am I done?
So, you put it back in,
Okay, so I put it in this, and then I do what?
wait a little bit and see if it changes.
Ah, okay? You wait a little bit and see if it changes. Right? When the thermometer stops changing, that means what is the same temperature as what?
Thermometer is the same temperature as the water.
Thermometer is the same temperature as the water, right? And when I bring it out here, I look at it, and wait for it to stop changing, which means what?
It's the same temperature as the air.
Okay, that's what a thermometer is. A thermometer is a portable system that you put in contact with other systems to see if they're in equilibrium. That's how thermometers work. Okay? A thermometer is a little equilibrium tester. And what I'm assuming when I do that is if the water is in equilibrium with the thermometer and the air is in equilibrium with the thermometer, then what? Are in equilibrium with one another. This idea, which seems kind of painfully obvious once I forced you to explain it, is actually a law of physics called the zeroth law of thermodynamics. Okay? Why is it the zeroth law of thermodynamics? It's the zeroth law of thermodynamics because there was already a first and a second law, and we realized that in some sense, those two laws didn't make any sense until we were very clear about what it meant to measure the temperature of something. So the zeroth law of thermodynamics is a statement about what it means that there can be something called a thermometer. And then the statement goes something like this. If, two slightly different ways to phrase it, let me pick one. If two systems, A and B, are each in equilibrium, I'll say thermal equilibrium, so we know we're not talking about chemistry. Thermal equilibrium with a third system, C. Then A and B will also be in equilibrium with one another. Placed in contact. Meaning, no heat will flow from A to B if you put them together. It seems like a very technical and almost unnecessary thing to say, but it's the equivalent of, at the beginning of inventing mathematics, having to say out loud, A plus B equals B plus A.
It's like Star Wars without the whole.
Yeah. Well, I mean, nothing else makes any sense without it, okay? Because we can't define that there is this thing called temperature unless equilibrium has this transitive property, that two things in equilibrium with a third will also be in equilibrium with another. So I know that if this reads, okay, 19 degrees, and there's a chunk of metal in the laboratory that's also 19 degrees. If I put that chunk of metal into this water, they won't exchange heat with one another. They will be at equilibrium with one another. So that's the zeroth law of thermodynamics. It is a formality, but it's absolutely necessary that this idea of temperature makes sense. So temperature is a measure of kinetic energy, and it's a measure of equilibrium. Now, if I take two things that are not at the same temperature, they will transfer kinetic energy from the molecules of one to the molecules of another. How do we characterize that? How do we define this transfer of energy from one thing to another? That's what we call heat. Okay? And the definition I will give you for heat is very, very picky. I'm not going to demand you always be this careful about the word heat, because I'm not always this careful about the word heat either. But this is the definition of the word heat. Heat is energy transferred from one system to another. Due to, or as a result of, their difference in temperature. Where temperature is what? Temperature is, to define it as precisely as we need to for this class, is a measure of the average kinetic energy of the atoms and molecules in a system. Okay. Now let's definitions a little bit to see where the pitfalls are, see what we don't want to say. Much like I harped on the fact when we talked about the difference between force and impetus, that force is not something you have. Force is something that happens between two objects. Heat is not something that a system has. It's tempting to say the difference between spilling the venti Starbucks in your lap and the tall Starbucks in your lap is that the venti has more heat. No. We don't want to say that. It has more total thermal energy, but it doesn't have heat. Heat is not a thing you have. Heat is a way of transferring energy from one object to another. It is a
exchange.
Heat is an exchange, right? Heat is the energy transferred. It is not a kind of stuff, and it is not something you have more or less of. It's really, really hard to always be that careful about the word and to not use it as a stuff. It's very hard not to say the...
So it's always a relative.
Well, it's always...
Because like I don't have any heat, but relative to like the air around me, I have heat.
Well, you can heat the air around you by transferring energy to that air, right? The heat is the energy absorbed by the air.
Right.
Okay? You didn't have it and give it to the air, right? The heat is sort of that transaction that happens between you and the air. Just like force, right? If somebody punches me in the face, they don't give me a force, right?
Right.
There is a force exerted between the two things.
Right.
Heat is very much like that. It's a transactional word, not a stuff. Like I said, it's really hard though not to say what happens if I take this hot block of brass, which is now, holy shit, 102 degrees Celsius, and I put it in this cold water. What happens? It's very tempting to say that the brass transfers its heat to the water. Okay, that's not exactly the way to say it. Okay, you can say the brass heats the water, or the heat exchange between the brass and water equals so and so many joules. But you shouldn't talk about the heat like it's a stuff, okay? Because it's falling back on the caloric model where we thought of heat as a substance. It's not exactly the way to think about it. But it's very, very tricky much more trickier, I think, than force, to not talk about heat in that substance talk, to not fall back on the idea that there's a thing that's being transferred from one to another. Okay, the thing that's, if you want to talk about a thing being transferred from one to another, it's the thermal energy. It's the sum total. If we want to put one more definition here, total thermal energy It's the total kinetic and potential energy of all the molecules and atoms in a system. An object has thermal energy. This hot block of brass now has more thermal energy than the liter of water over there. It does not have more heat. If I put it in the water, it will heat the water, but it does not have heat any more than it has force. So that's a pretty nitpicky bit of definition, but necessary if we're going to make sense of these
So when
orders.
thinking about heat, you really should just think about like radiators, right? Something that's giving thermal energy to the space around it.
Yeah, I mean,
That's having that fight.
yeah, I mean, heat only comes into play when two things are different temperatures, right? Heat is only something that happens to objects that are not the same temperature, whose atoms and molecules don't have the same kinetic energy, and so they will transfer energy from one to the other. Heat is not,
So when a system has two different temperatures, there's heat.
there's the potential for a transfer of heat between them, right? I mean, it doesn't, we haven't talked about how fast it's transferred, or how much it's transferred, or what rate it's transferred, but there's the potential for heat to flow spontaneously from one to another if two parts of a system or two systems are in contact with one another and are at different temperatures from one another. And then the question becomes, how do we quantify this thing that we call heat? And how is it related to the thermal energy, which depends on how much stuff there is? For example, one of the reasons I've got a bunch of beakers full of water here is we can ask the question, suppose we have two systems with the same amount of stuff. Here I've got water at, well, I wish it was 20, it would make the math easier, but, well, it's a little more than 19. Let's say 20 degrees. So I've got a kilogram of water at 20 degrees Celsius.
What's that in like liters?
It's exactly 1 liter. Water is,
Kilogram is a liter?
yeah, a kilogram of water is at a particular temperature. I mean, that's kind of where the definition of kilogram comes from, or definition of liter comes from, I guess. And suppose I have some other kilogram of material, like a kilogram of brass, at, well, let's just say 100 degrees Celsius to round it off. It's a little bit warmer, but by the time I put it in the water, it'll cool down probably by a couple of degrees. So it's a different color. So this is a kilogram of brass at 100 degrees Celsius. If I put these two things in contact with one another, what might be my naive expectation for the final temperature of this system, and why?
An average of the two.
Okay, which would be what?
Maybe no, 70.
60, right? The average of 120, 100 plus 20 divided by 2
Yeah.
is 60 degrees. That naive expectation is based on what? You've got the same amount of, here's the water at 20 degrees. Here's the brass at 100 degrees. If they're the same amount of stuff, you might expect their change in heat, well, don't want to say that. You might expect the amount of heat transfer, the amount of heat given to this and the amount of heat given up by this to be equal so that they meet here at the middle at 60 degrees. And we can do it. It might take a while. I'll have to talk while it's happening. But the first thing I'm going to do is put this in the styrofoam container instead of the glass container. Why do you think I'm doing that?
The glass.
heat or, I mean, but.
I mean, that's something to do with insulation.
Yeah, I'm trying to eliminate the effect of the air in the container on it, right? Because the
Right.
air is going to absorb some of the heat, the container is going to absorb some of the heat, and we want to minimize that effect by putting it in something insulating. What do we mean by something insulating, by the way? What is that? What am I talking about?
Yeah,
Doesn't transfer the energy what?
The insulating, thing doesn't absorb any energy or
yeah, I think that's something to do with absorption.
Does it not absorb any energy?
Very low.
less than the other.
What's the operative word that we're missing here?
There's less transfer.
Close. There's less. What do you mean by less? I think you know it, you're just not saying the exact word. Look, if I want to keep my lunch cold, I put it in one of these styrofoam containers, right? It's going to stay cold forever?
No.
No. So what's different about the rate that the heat is transferred?
Slower.
Slower, right? Something is insulating if the rate at which it allows the heat transfer is slower than something made out of metal. So if you look at this right now, I'm just going to check the temperature real quick. It is... right? Oh, it's 22 degrees. I keep track.
How do we decide how long?
22 degrees. Well, I have to keep checking it to see when it stops changing.
No.
So I'm going to have to talk and think and check the temperature every few seconds. I'm going to tax my multitasking ability, but I'll do the best I can.
How does glass work?
How does it work in what sense?
Well, it's like a liquid, right?
It has some properties of liquids in that it's not a solid crystalline structure. The molecules are free to very slowly move past one another a little bit. So it's
It's a little more slippery.
yeah. Seriously? Not going up any more than that? Still in 22 degrees. Let's leave that property of glass aside for a minute, because there's another thing I want to talk about in terms of properties of things. Since we're waiting for this to heat up / cool down, I want to talk about this idea of the rate of heat transfer from one thing to another, because it's really, really important. For example, suppose you come out of bed at night and you're going to walk to the bathroom. Okay? You are, in general, unless there's something wrong with you, at a temperature of around 98 degrees. Okay? The floor is probably at a temperature of around 70 degrees, depending on how warm or cool your house is. Your floor, however, is in equilibrium with the air. So whatever temperature the air is, the temperature of the floor is the same. Suppose you've got carpet. What's the temperature of your carpet? 70 degrees, right? What do you feel when you walk from the carpet to the tile? It feels cold. Why?
Because there's a transfer of your energy to the floor.
Yes.
Is there not a transfer from your
Well, there's a rapid.
faster, right? It is the rate at which heat is taken away from your body that you're feeling when you feel the difference between the carpet and the tile. Okay? It's not that the tile is colder than the carpet. It is that, it's not like Francis.
Bigger leach.
It's not like what Bacon was saying about, things made of wool having inherent warmth. That's not it. Your carpet is not inherently warm. It's no warmer than tile. It is how fast it transfers that heat to you. Same thing goes to the difference between the steering wheel in the summer in your car that's 120 degrees and your seats in the car, if they've been in that same car, they're also 120 degrees. But if the steering wheel is made out of hard rubber or hard plastic and the seats are made out of soft, cushy fabric, one of them transfers heat to you more quickly than the other. We got 24 degrees now. And so it's a question of the rate at which the heat is transferred from one object to another. This property of a substance is called the thermal conductivity. How fast or slow does it allow changes in temperature to happen? How quickly does it give up or absorb its heat? And a lot of the perception we have of how hot or cold something is related as much to its thermal conductivity as it is related to the actual temperature. Because we are, in the environment in which we typically do our business, we're quite a bit warmer than everything around us. We're 98 point some degrees. We're usually doing our business in an environment that's 70, 50 degrees or so. And so what we're perceiving when we put our hand on a piece of metal, we put our hand on a piece of fabric, is how fast that object is absorbing heat from us and how fast it's cooling our surface. Oh, was it 26 yet? It's almost 20. No? Still only about 24.
So what's going on there?
Well, it certainly doesn't seem to be heading to 60 anytime soon. Look, this thing was boiling when I put it in there. I don't know. I mean, is it hot enough?
Lost a lot of heat though from just the swing from there to there.
Yeah, probably not more than a degree or so. I mean, can I touch this thing yet? Yeah, I mean, this is not hot anymore, right? So
Yeah.
it's not. It's certainly not 100 degrees. It's certainly not
That's
boiling.
brass.
It's brass, right?
Is that like different metals have different conduction rates, right?
Well, conduction isn't going to explain its final temperature, right? Just how quickly it gets there. So that's not it. It's not just the conductivity. It's that somehow the water seems to have won this fight, right? That we started with a kilogram of water at 20 degrees and a kilogram of metal, brass in this case, at 100 degrees, and the final temperature winds up around something like 26 degrees. Why?
Water stubborn.
Yeah, it seems like these two substances have a different amount of,
Conservation.
well, not conservation, because, I mean, look, we're not saying that energy conservation is violated here, right? I mean, one of them cooled down, the other one warmed up. It's just that this one cooled down, this one warmed up 6 degrees, and this one cooled down 54, no, 74 degrees. It seems like the water can hold more heat at a given temperature than the brass can. We call this property of a substance its heat capacity. Different substances at the same temperature have different amounts of thermal energy and can therefore absorb different amounts of heat than other substances. Water, it turns out, has an enormous heat capacity compared to most solids. Which means it takes more energy to change the temperature of water than it takes to change the temperature of brass. Okay? Changing the temperature of water by a degree is way harder than changing the temperature of brass by a degree. This is a fact about the material, about the substance. We can look up, you can go online and look up a table of specific heats to see how much they vary from substance to substance. And we can look up, for example, various different metals. And we can look up water and see how they compare. Specific heats of solids. specific heats? Aluminum, 0.9, bismuth, copper, brass, 0.38. So what are the units here? It's joules per gram degree Kelvin. So the specific heat of brass is 0.38 joules per gram per degree Kelvin. What does that mean? 0.3, was it 0.38? That means it takes 0.38 to raise the temperature of 1 gram of brass by a degree Kelvin, which is the same size as a degree Fahrenheit, right? Fahrenheit and Celsius degrees are, Kelvin is the same as Celsius. The size of the degrees is the same. So heating up the brass from, or let's say cooling down the brass from 100 degrees Celsius to 99 degrees Celsius, each gram releases 0.38 joules. Okay, aluminum is 0.9, copper is 0.38, gold is 0.1, silver is 0.23. When thinking about something like cooking, okay, and looking at that table, which do you think is better to have your pots made out of, copper or aluminum? Probably copper. Why? Right, less of your energy is going into heating up your pan, right? Your pan is going to heat up faster because it takes less energy to heat it up compared to something like aluminum. I mean, gold would be even better, but we don't all have money to have pots and pans made out of gold. Yeah. Look at water, though.
What does this mean, though, that you could turn the heat off on the aluminum?
And it would stay hot longer. That's another issue. But look at water. Specific heat of water is 4.186 joules per gram degree Kelvin. Okay? That is almost 12 times more than the specific heat of brass. Means it takes 12 times more heat. Yeah, I can say it that way. It takes 12 times more heat to change the temperature of water than it does to change the temperature of brass. Which means that if this changed temperature by 6 degrees, and this changed temperature by what? 74 degrees, I'll be goddamn, look at that. What's 6 times 12? 72, right? I mean, so with our half-assed experiment, we got the right answer, which is the amount that the water changes temperature should be about 1/12 the amount that the brass changes temperature, right? Because it is that much harder to change the temperature of water compared to changing the temperature of brass. That's pretty impressive, actually. I'm kind of stunned that that came out so well. What does this mean about water? Well, it means water is hard to change the temperature of compared to a lot of other substances. This has a lot of, it has a lot of implications. For one thing, if you look at the ocean temperature compared to the air temperature as it changes seasons, the temperature of the ocean changes way less than the temperature of the water, both because the volume of the water is pretty big compared to just the mass of the air, but also because water has a greater specific heat. It takes more heat to change its temperature than air. It also means water is good for cooling. Well, yes. I mean, it's a good thing to be made out of because it means that your temperature fluctuates less with the environment than if we were made out of, copper. And when outside, our temperature would be, 12. It would change 12 times faster. We would lose heat to the air 12 times faster. Well, not 12 times faster. That's the wrong thing to say. Is that it would take 1/12 the amount of heat to heat us up, and 1/12 the amount, and we would give off 12 times as much heat at a given temperature to the air. When we're in contact with the air that was a colder, like today when we go outside and the air is 40 degrees or whatever, when we're outside giving off heat to the air, or to use the really precise nitpicky definition of the word heat, we are heating the air because we are warmer than we are.
I've always said that, like, in nightclubs, it's like there's just a shitload of 98.6 degree radiators.
Oh yeah, well, and if you think about it in terms of just energy output, one of the calculations we do in the energy and sustainability class is just in terms of the energy output of the human body. I mean, if you know, how many calories do you eat in a day? Figure. 2000s. Oh, 2000s. Oh,
Depends on your size
depends on your size and your level of activity.
and your country.
2000, and yeah, I mean, 2000 is probably a pretty good estimate for most people. If you're not on a diet and you're not like training for a marathon or something, you know, someone like
And then you should eat more.
then you should eat more, right? I mean, someone like I think in the last Olympics, Michael Phelps was, you know, his calorie intake was like 7,500 calories a day or something.
They said anywhere from that to like 13.
It was ridiculous.
On what days?
But for most of us, it's around 2,000 calories, and that's actually kilocalories. Food calories are 1,000 calories each. So if you eat 2,000 calories is on the label of your food, that's 2,000 kilocalories per day in joules. Well, 2,000 kilocalories per day is it's power, it's energy per unit time. 2,000 kilocalories per day is 96.8 watts, which means you are all the time metabolizing energy at about the rate of a 100-watt light bulb. So having a room with 200 people in it is like having a room with 200 100-watt light bulbs in it. The same amount of thermal energy is being converted from chemical energy to heat. And we're doing that all the time. So, you know, on average, you are burning energy at the same rate as a 100-watt light bulb. If you are jumping around, dancing, running, doing something else, you're probably doing about twice that. So you have about 200 watts of energy are being, you know, radiated from you as heat.
There's this. Have you heard of Herschel Walker? He used to be a running back in the NFL
Yeah.
back in the 80s. Now he's like becoming an MMA fighter.
Oh, geez, okay.
He's a very odd guy. He said, I think he had like split personality disorder. But he says that that he every day he's a vegetarian. All he has is a salad, like bread and soup.
What kind of soup?
Yeah.
I don't know, but he's a
Hope it has
vegetarian.
protein in it, 'cause that's a problem.
Yeah, and the guy's like 215, 220 pounds.
Well, I mean, that's
It
not
sounds like he's
impossible.
probably lying.
Yeah, I mean, it seems like if you're being that active, you're going to need more calories than that. But yeah, I mean, you know, bread could mean like 8 loaves of bread. I mean, it doesn't.
Yeah.
As long as it's not being clear on the volume of it, that could certainly be true. You know, it's for the purposes of physics. All that matters is the number of kilocalories that go in and the number that you use. It doesn't matter so much the form in terms of your metabolism. It's a difference whether they're carbohydrate calories or fat calories or protein calories and so on. But in terms of conservation of energy, all that matters is the amount that go in has to equal the amount that you use, or you'll start storing it up, or you'll start using it from stored energy somewhere else. So this idea of specific heat is, it's kind of hard to get your head around, especially when you start sort of asking yourself, well, why? Why does water have a different specific heat than brass? Why does copper have a different specific heat than aluminum? It's really not clear how to answer that without delving really into the intermolecular properties of the material. In other words, what's going on with those forces? I erased the word potential energy, but what's going on with the potential energy between those molecules?
Even in your body that's going on. Like muscle and fat release energy in different rates. as well.
Yeah, I mean, that has to do with how your cells are metabolizing those chemicals and converting the energy in those chemical bonds into energy in your cells, and ADP and ATP and things like that. I mean, the details of how your body metabolizes organic molecules are far beyond my ability to talk about intelligently. Once the biology professors start drawing the little ADP and ATP molecules on the board, my brain just shuts down. Anything bigger than a water molecule, and I'm not interested in it. That's what physicists. I'm concerned with things smaller than that, not bigger than that. But just from a pure mechanical standpoint, if you've got a lump of copper and a lump of gold, why do they absorb heat differently? Why do they have different amounts of heats at different energies? One of them has to do with just how big the atoms and molecules are, how heavy they are. Something with heavier molecules takes more kinetic energy to get them moving. Some of it has to do with what are the forces between those adjacent atoms and how much energy is stored in the bonds between those atoms. It's not a simple matter. You can't just, well, without quite a bit of experience in material science, just look at the periodic table and guess which elements will have a higher specific heat than others. It's a purely experimental thing that we figured out by heating up and cooling things down and making the measurements and seeing which ones have the bigger or smaller specific heats. What this means, though, is if we wanted to calculate, if we wanted to determine the answer to this question without just guessing, we would have to know the specific heats beforehand. The way we would do it is this. If we wanted to know the final temperature of the mixture, what we would say is that the change in energy of the water equals the negative of the change in energy of the brass. Or equal and opposite. Whatever energy the water gains, the brass has to lose. The energy, it turns out, transferred by heat is equal to the mass times the change in temperature times the specific heat. And we'll often use the symbol C sub P for specific heat. It stands for specific heat at constant pressure. There's also specific heat at constant temperature, and I do not feel the need to explain to you why there are two different ones and what they mean. So this for the water is equal to mass times the change in temperature times the specific heat for the brass. That's how we would actually solve the problem. For our purposes, the mass of the water was 1 kilogram. The change in temperature was the final minus the initial, which is 20 degrees was the initial. The specific heat of water was 4.186 joules per gram degree Celsius. And that's going to equal the mass of the brass, which was 1 kilogram. I chose a kilogram chunk of weight from the lab just so that it'll make this easier. Times the change in temperature, which is the final temperature, minus 100 degrees, times the specific heat of the brass, which is 0.38 joule per gram degree Kelvin. And then we've just got algebra. 4.186 times t minus 20 equals 0.38 times t negative 0.38, t minus 100. My calculator. So 4.186t minus 20 times 4.186, 83.72. 8's gone completely out of control. 83.72 equals negative 0.38t plus 0.38 times 100 is 38. I'm going to calculate for that. 4.186 plus 0.38. 4.186 plus 0.38, oops, 4.186 plus 0.38 is 4.566. T equals 38 plus 83.72. 121.72. Oops, 121.72. So T equals 121.72 over 4.566. Boy, I hope I did this right. Divided by 4.566 equals 26.6. How do we account for the fact that we only got 26 and not 26.6? Well, first of all, our thermometer doesn't even read down to the 10th of degree. That's one problem. Second of all, are we wrong in the right direction? In other words, did we get the answer wrong in the direction we would expect to get it wrong, given the crappiness of our experiment?
Yeah,
Why?
because it would lost, heat going from that place to that place.
Right, and probably lost some heat to the styrofoam, and probably lost some heat to the air inside that little box. So we would expect our real answer to be a little lower than the pure predicted answer, assuming absolute conservation of energy. Because that's what this expression is. It's saying that the only change in energy was the brass lost energy, the water gained energy. Of course we know that's not true. The styrofoam probably warmed up a little, the air warmed up a little was given off to the air when I carted across the room on the stream. So when doing experiments, it's important. I mean, you're probably always told to do this when you did lab experiments in high school. Identify your sources of error. In other words, what kind of things did you screw up to give you the wrong answer? But
CP, I'm sorry.
what's that?
CP.
Specific heat at constant pressure. I could just use C for specific heat, but there are different ways to measure specific heat, and they give you slightly different answers for different materials. When we're talking about solids, we're almost always using specific heat at constant pressure. It's important when you do an actual experiment to ask that if you're wrong, are you wrong in the right direction? In other words, are you wrong in the direction that you expect your assumptions to push you towards the wrong answer? So that's how you do specific heat problems. We may do other ones, we may not do other ones. But the idea is that when something changes temperature, it's not as simple as just how much of the stuff it is times the change in temperature. That there is this factor called the specific heat that tells you how much energy is required to change the temperature of that substance. So I think we've got as much of a handle as we need to have on the terms heat and temperature, at least to talk about heat in the way that we need to talk about it. The question is, what do we want to do next? What we want to do next is, first of all, prove to ourselves that we're right in thinking about temperature as the motions of atoms and molecules. In other words, what does the kinetic model of heat give us that the caloric model of heat did not give us? Because people knew about this stuff when they were doing caloric theory. This is as old as the early 1700s. People knew that there was this thing called specific heat. People knew that water was harder to heat up and cool down than metals, and that if you put different metals in water, the amount that it changes the temperature of that water is different depending on the metal. That's nothing new. You can explain all of this just as much in terms of caloric. What it means for something to have a greater specific heat is that it has more caloric, it can hold more caloric at a particular temperature than some other substance. What we want to know is, can the kinetic theory of heat tell us anything new about heat? In particular, can it explain any of the whys of the laws of thermodynamics? In particular, the fact that heat only spontaneously flows in one direction. And can it explain for us, can allow us to make predictions, precise predictions about what happens in a physical system when heat is transferred from one part of the system to another. So where we're headed is for an exploration of the full modern theory of thermodynamics, which combines the idea that heat is motion with treating heat statistically. In other words, if what's happening in this water is that there's a trillion atoms and molecules moving around, how do we talk about those trillion atoms and molecules quantitatively? We can't possibly hope to write down the velocities of all trillion of them. So what do we do instead? And we'll talk about next time the idea of statistical mechanics as a replacement for kind of classical determinism, moving us a little bit away from the Newtonian